All right. Hello, everyone. Welcome to the final workshop on day one. My name is Faraz, and I'm one of the co-organizers here at TMLS. We are extremely thrilled and pleased to host the team from Integrate AI at this workshop. Just before we get started, if you do have any questions, please feel free to ask them in the chat with the queue in front. This workshop is being recorded, so we'll be able to share the recording and also the materials after the summit. If you are joining us for the talks on the 17th and 18th, please look for an email sometime later tonight or early tomorrow. So without any further ado, I'm just going to hand over the virtual mic to the team. So welcome.
Perfect. Thank you. Thank you so much, Faraz. We're very excited to be presenting at TMLS this year. We're excited to be sharing some of the tech that we are working on in-house and just get you all up to speed and familiarized with it. My name is Ro. I'm our VP of Machine Learning Products. I've been with Integrate for 4.5 years now. On this call are my colleagues, Elliot and Ron. I'm just going to hand over to them quickly so that they get a chance to introduce themselves. They'll be helping through this workshop as well. So it's good to know their names and faces in case you needed anything.
Sure. Hi, I'm Ron. You'll see me as Nasron on the list. I'm one of the main engineers here at Integrate AI. I'm working in Federated Learning, and I'll be helping you guys through the workshop section of our presentation. I'll pass it over to Elliot.
And hi, everyone. Great to meet you. I'm Elliot, Product Marketing Manager at Integrate AI. I'm not the expert. Nasron and Ro are the two experts, but I will be here to support throughout the workshop.
Perfect. Great. With that, let's just jump in. So I thought it's worth it to just start with who we are, what our areas of expertise is before we start jumping into the conversation. We are a VC-backed AI startup. We've been around for roughly 5 years now here in Toronto. We've raised some money. We are majorly focused on building solutions that goes across different data sets that cannot otherwise be joined with each other. And our mission is to be able to help companies build AI technologies that essentially allows them to have mutual benefit between them and their customers, and that it would benefit from the network of data and essentially enhance collaboration. We have won some awards. I guess that means that people believe we're on the right track. We're very privacy focused. And that is why you will see us talk a lot about that today in the course of the workshop. In terms of what we have in mind for you today is we essentially want you to walk away with a few things. We are huge believers that data is locked around the different organizations, even within the organization, and that data holds a lot of power. So today we will be introducing to you the concept that is siloed data and why it matters. Then we're going to shift a little bit of gears towards a solution that we have in-house that is mostly geared towards making machine learning models better with such siloed data, and where the applications are for that. That's where we get deep into federated learning. And then at the end, we're going to be doing a hands-on workshop where it's about you getting your hands dirty on how this technology actually works. With that, we have put together an agenda where we will first walk you through the world of multi-party computations. We will tell you about our solution that is federated learning. We're going to go through the on-hands workshop, and then we would love to spend some time in the discussion mode so that we can talk about what were some of the challenges you saw, and where are some of the cool technologies that come in to help with those challenges. We also have an early access program for a product that we're releasing soon. That is our federated learning product that is coming out soon. And if you heard or saw something that was interesting, we would love to have you on that wait list. We are signing up for that program right now. With that, let's just jump in. So our journey starts with believing that intelligent systems require diverse and relevant data sets to become better. And as the enterprise world has shaped, there are very few teams that can get there alone because this data exists between different companies and even between different teams within the same company. With that, we introduced this concept that is the siloed data. The siloed data is the name that we have given to the data that cannot come together and get centralized due to one of the following reasons. Either there exists a trust barriers between the different companies that would prevent them from being able to directly join data sets with each other, or there are ever increasing regulatory barriers that essentially keeps people from being able to track individuals across the web, putting more protection around the consumers, as well as being very tight on enterprises on how they use and access data. There's also the problem of unknown business impact. If you're a data scientist on this call, this problem is going to probably resonate with you, that you want to access some data somewhere within your own company or outside of your own company. And the first question you're asked is like, what is the business impact that it's going to bring? And the answer is, I don't know, I need the data first. But because you can't make that argument, you can't make the argument for the risk that your company will be taking. And therefore, most of these projects don't even get off the ground. There are also a lot of technical difficulties associated with bringing the different data sets together. They live in different environments, different databases. The way to share and merge data is not that trivial. And these all make it very hard to bring the siloed data together, which is the blocker to having more data available for intelligence. So let's talk a little bit about the use cases that people actually use this system, these siloed data for. One common thing that you will be hearing about is multi-party query, which is when an individual, a data scientist or a business analyst cares about being able to find a particular individual across the different data sets that exist potentially across different organizations. And the reason they care about this is because the interaction with the user lives in one environment and the actual outcome of what happened with that user lives in another environment. A very common place for this is the ad world, where a user sees an ad online, but they go off and purchase within some enterprise, and this dot never really truly gets connected. In the second realm of what people would want to do with siloed data is understanding statistical properties or features or attributes about different users. So this is where multi-party computation comes in, where there is different information about different portions of the populations living with different entities, and a data scientist or a business analyst cares about being able to extract that information. The last but not least is about training machine learning models, essentially getting further down the chain of automation and incorporation of AI in the systems, where a machine learning scientist or machine learning engineer cares about being able to train a machine learning model on top of data that they don't have access to. So these are some of the places that we have seen most interest in being able to access other sources of data. So the thing to note is there is no silver bullet. There is never really a solution that would go across all of these different use cases, solve all the problems or all the risks or all the considerations that come with each of these use cases. And therefore, the thing that we're going to be trying to do in the next 15, 20 minutes is just give you a general overview of the landscape. What are some of the solutions that exist, so that you can figure out, or you can start asking the right questions of what is the right solution to the context that you have. So let's talk about a little bit, like we went through the landscape of use cases. Now let's talk a little about solutions. So we talked about multi-party query. Recall that this is about finding an individual across the different data sets to be able to perform some sort of calculation on top of it so you can figure out a particular measurement. The solutions in this world are mostly around clean rooms or safe havens, if you have heard about them. To talk more about what these solutions actually do, I would like to start with a use case. So let's say that I am a machine learning scientist within a retail store. Pick whichever you like, Home Depot, Canadian Tire, what have you. And what I care about is understanding the attribution rate of ads without having to receive or give my data to the media company that is doing my ads. Let's say this happens on Disney Plus or wherever else that it could happen. So one company owns the data that has to do with interactions, what products were purchased, and the other one has data about what the user actually engaged with and what they saw. The way clean rooms work is that they often have this trusted party sitting in between that is going to take some hashed version of the data from the two other sides of the party, do a join, figure out what is let's say, the number of people that exist that saw the ad and made the purchase, and essentially give back the calculations on top of this data to the users that made this query. This is what the safe havens and the clean rooms are based off of. So there exists a trusted party that can see some version of the hash data to do some calculations. In the next portion of the landscape where we had multi-party computation, probably one hot keyword that you have heard about is secure multi-party computation. Let's start with a use case with that as well. So recall that the thing that mattered here was being able to calculate some general set on top of the different data sources that were distributed across. So what I care about is I want to know, for example, the top 3 purchase items, price for the top 3 purchase items in apparel for users between the age of 18 to 24 without having to move the data around. And I essentially have 10 retail stores that have agreed to participate in this network. So in the secure multi-party calculation, what ends up happening is, let's walk through an example. Let's say I have 3 people, Ali, Brian, and Caroline, and they essentially each have a certain income rate per hour, right? Ali has $100 per hour, Brian has $200 per hour, and Caroline has $300 per hour. Let's say that these people have agreed to participate in the network, but don't want anyone else within the network to be able to say how much each of them individually make. In this case, Ali essentially takes a random seed and takes their income apart such that the summation of those numbers give the value of their income, but none of those individual numbers give anything away about their income. Brian does the same and Caroline does the same, and they now distribute each of those parts to the other peers within the network. Then what happens in this case is that there requires to be a central server that then takes those broken apart pieces from each of these individuals and takes the average across them or takes the sum across them. This way, no one is going to know what any of these individuals participated into the network, but as a total, they all get back the average or the sum of the network. You also hear about homomorphic encryption in this landscape, where instead of what we talked about, which was having a mathematical way of hiding information, essentially there is a particular family of encryptions that come into place. This is where a data owner essentially creates 2 keys, one public key and one private key. They encrypt their data with the public key. It goes onto the server. The server can do computations across the people who have put data in that trusted data storage. The server would have no visibility into what that data was. They're actually operating on encrypted data. And once the results are ready, they can send the results back to the different data owners, and they can decrypt this results using private keys. And that can also be one form of how this happens. So if I were to tie it back to the initial use case that we brought up, which was like figuring out the top 3 purchase prices across the different retail stores, these 2 ways are ways that a data scientist could use to be able to get that value back without having to directly share their data. And in the third family which was under the distributed training, which is essentially you're a machine learning scientist or a machine learning engineer, and you want to be able to access different data sources to perform some sort of training, there is the federated learning framework. What the federated learning framework allows a user to do is, here the question differs, right? The question is no longer, I need to understand data. It's more about, I want to train a machine learning model across these different data sources without data having to move. And in the same example, let's say that we want to essentially predict the likelihood of conversion without having to move the data across the 10 retail stores. This is where federated learning can come into place. And the way the federated learning system works is that it essentially takes a bunch of machine learning models, sends them to where data exists. So data is not moving across the different nodes, but the machine learning models get deployed to be close to the data. They train there. The thing that moves across the network are parameters, gradients, or information about training. So things like the loss value that comes back to a global model, to a central server that then calculates the average or some other mathematical function on top of these models to get the better model trained across the network. And with that, a machine learning scientist can achieve their goal without having the data to move. Now, I portray each of these solutions as different to like one of those categories. But the thing that is important to know is that the lines are actually a little bit blurry, because you could have a federated learning model that then gets biffed up by getting a homomorphic encryption on top of it, such that the server cannot see the gradients, but can still do the calculations and for the system to be a federated learning homomorphic solution. You could have a situation where people use the admin access, which was like under the category of safe havens that we talked about, to essentially dice the data in the right way to perform analytics. So those things do exist in the industry. However, the thing to note is that whichever of these you bring, there are pros and cons associated with them. So safe havens and clean rooms, they're based on access control mostly and encryption, hash encryption. They're mostly suitable for cases where you're trying to track individuals to see whether they took some action or not. What makes them not great for cases of machine learning is that it's increasingly difficult to set the right setting, admin control setting, and it's very hard to measure privacy or security impact. The secure multi-party encryption, it allows blind calculation across peers. There is no need for a trusted server. It works well for certain calculations, and manipulated data can move around, but it's computationally expensive. As you saw in the example, even with 3 parties participating in just 3 values, the calculation exploded into 9 numbers getting moved around and needing to perform operations on it. Now, you can see that exploding with the number of silos expanding and with more data. The homomorphic encryption allows simple blind data guarantees, and there's no need to trust the server, and encrypted data can move, but bear in mind that it can only be used with certain operations, namely multiplication and additions, and it is also computationally expensive. And last but not least, federated learning allows for training machine learning without data moving, but there are also complications involved with that, which is like you're training a machine learning model without seeing the data. There are privacy considerations to be had, and the question is like, how do you extract value from a system like this? So before I move on any further, I want to pause here because we're going to now shift gears to focus on the federated learning system. Any questions, any comments before we move on about the content we presented so far? Okay.
And I just want to jump in and say, if anyone has any questions, feel free to drop them in the chat also, and we'll take a look at those as well, and we could respond to those throughout the presentation.
Perfect. Yes, that's a great point. Okay, so let's now talk about what we're focusing on in this session. In this session, we're going to be focusing purely on the federated learning solution that we talked about. The main reason being that we are a company focused on improving machine learning models and machine learning models performances for across a network of data. And that we believe that it has some very neat properties that can enable a bunch of use cases that would not have been possible without it. So let's talk about when is federated learning the right tool. The thing to note is that at the heart of it, your problem needs to need more data to improve the performance of a machine learning model. Now, this lack of data might show up in different ways. Either there isn't enough data, for example, cold start problems, where, let's say in an online application form sign up, there's just not enough users for someone to be able to train a conversion model, right? Like by its nature, there's not enough data. There could be not enough data just because the nature of a business, right? There's like auto dealership data that by its nature, there are not those many people buying cars per year. So there's not enough samples to be able to train a model. The other family of issues could be that there is a population bias in the data. So let's say that the retailer has the average customers of age of 18 to 24, and they don't have much visibility in any other age group, and they care about being able to gear or target those users within their user base better. Or that's like some new company is expanding business in a new area, so they don't have information about that population to be able to make good decisions. Or for example, even in less businessy situations, like images for image recognition in the retail case do not have all of the products information to be able to train on those. In the other family of not having enough data, there is a treatment bias in the data. So there is a bias in the actions taken or in the labels available that does not allow the model to be the best performing model. For example, in the healthcare use case, it might be that a hospital specializes in a special type of cancer, so they only have access to certain labels within that environment. Or there is a new campaign rollout. There was never previously an action like this taken on a user. Or there's a new product rollout, but this product exists in other environments and someone is trying to roll them out. So these are the product conditions that might suggest, and also bear in mind that the data cannot become centralized. So it's not like parties are very willing to give each other data. So that's the other key portion that causes the data not to be enough. And the other piece to know is like, there is also an assumption that it's okay for the central server to be able to see some amount of information. In this case, it is the gradients in the training. This is true about the federated learning structure that I showed you. There are other frameworks for federated learning. There's even more in research, but this is the one that we have found most suitable that gives most of the access right to the right users. You will see in a few seconds once we start doing the hands-on what we actually mean by that. Any questions on the use cases? Okay, perfect. With that, I'm gonna hand off. This is where we're gonna be now starting to get our hands dirty. So I'm gonna be handing off to Ron to be walking you through the piece that is about setting the system up and seeing how it actually works. If there are no more questions, Ron, should I stop sharing and then you start sharing?
Sure. Just wanted to check if does anybody want to take a break before we get into this kind of a longer thing. We can take a few minutes. Otherwise, we can keep going. No. Okay. All right. I can get started. So let me get this thing up first. Right. So what we'll be talking about, just give you an overview of what's going on here, is that what we'll cover is that we'll kind of do a simple kind of hello world federated learning setup. It's going to be kind of purely, we'll do a kind of a local setup, which means like centralized. So what we basically want to do is compare a machine learning model that was trained on all the data versus a machine learning model that is trained with federated learning, just to get an idea of where it works and where it doesn't work, just to get some, so that everybody understands some mechanics. Then we'll talk about one of the federated learning problems, which is the IID issue. And so IID meaning independently identically distributed data. So this is about how FL can have issues when the data isn't correctly distributed across all the silos. So you can have sort of skew between the different silos, and it can cause problems with the model that's trained. And so we'll go over that. We'll test the local version, and then we'll test an FL version. We'll show some of the mismatch performances, and then we'll do that. And then we'll talk about privacy and security. So most of the federated learning that we're going to be talking about doesn't take into account privacy or security concerns. And so we'll talk about some of those situations. And then we'll show it, then we'll go through an exercise with a different framework that's about differential privacy without federated learning. And then we'll have kind of a group discussion session, right, where we'll break everybody up into groups. We'll talk about kind of infrastructure concerns and other concerns that we'll list out, that I'll give some talking points about what we can discuss. Ro and I will just jump between the different groups just to help give an idea of what actually has to just to help guide the discussion and get to know you guys. Right. So first is prerequisites. So Elliot posted a link to the prerequisites doc that I believe if you had registered, you would have received an email as well. And just wanted to check to make sure if anybody had trouble setting it up, do people have it up? You know, you don't have to have it set up if you're not that interested in actually you know, having to watch it. Like I'll be doing it, so you guys can just watch what it is I'm doing. Just a double check here before I get started. Okay, so no concerns. So yeah, so then we can get started.
Sorry, before we get started, can I get a thumbs up on people's Zoom if you have already done the setup? Just so that we make sure, because things would flow pretty quickly from here onward. I just want to make sure that no one gets left behind. Okay. Cool. Then let's get. Oh, we have a question.
Yeah, so the tutorial is actually meant to run in a terminal. It's not meant to run on Colab, and the main reason I did not structure it that way is because federated learning requires multiple services to run at the same time, requires a bunch of networking. So it works best within like an environment on your machine to run. So the Colab tutorial would work for the differential privacy stuff. So when you see that, you can go follow the link to the example, and then you can do that on Colab or a notebook of your choice. But to demonstrate federated learning correctly or easily, it usually requires a development environment. Any other questions? Right. Okay. So we'll get started. So first thing we'll talk about is a framework called Flower. So I'll just give you an idea here what's going on. So this is an open source framework that you guys can take a look at. We use this internally for the product that we're working on. And it's kind of a generic, it's a generic federated learning framework that is kind of geared towards both industry and research. There's a lot of federated learning frameworks out there that are more geared towards research. And this one is probably a bit of a good balance between the two, and gives users a good ability to just kind of customize what has to be done. So what it does is that it gives you the abstraction that you need to kind of train a local model on a client with some parameters. It lets you send the parameters from the client. So the client is like a silo, a data silo. Send the parameters from the client back to a central server, and the central server applies a federated learning strategy. So, for instance, fed average it's a popular FL strategy. So it takes all these received parameters from the different data silos, different clients, and it maintains a global model. Then it distributes the global model weights or parameters back to the clients. There's usually some kind of selection criteria for the clients. So this is like, there's cases where you may not want to distribute the model to all the clients, or you may want to sample some of the clients. Some algorithms do this in order to kind of help with the kind of some of the issues that happen with federated learning. And then we do this for a certain number of rounds. So if you train a machine learning model, you know that usually you have epochs in a train, where you're just basically doing the forward and backward propagation multiple times. It's a similar idea. You're basically sending a model to be trained, epochs on each of the clients, then bring the weights back, do some kind of averaging task, and then go back and forth, send it back to the client, do the work. It comes back, and we do it for a certain number of rounds until you get a model that converges, or doesn't converge, depending on how things are going. So why do we choose Flower? So why did Integrate AI choose Flower? There are other frameworks that exist. There's FedTorch, there's TensorFlow Federated, there's OpenFL, I think that's Intel's. There's quite a few different frameworks. And a lot of these frameworks are usually geared towards research, and sometimes they're very tied to a specific modeling library. So as an example, PyTorch and TensorFlow Federated are obviously tied to their specific libraries, right? You can do, if you use FedTorch, you're doing PyTorch with federated learning, and it's specific to PyTorch. If you do TensorFlow FL, it's specific to TensorFlow. So what we want is, what we wanted to integrate is that we want abstractions for separating the modeling from all this networking mechanics, like how you send your weights between your client and your server. You want a good separation in order to be able to test like multiple modeling libraries or develop your own modeling libraries or your own strategies for the federated learning. So you want that separation, which is why we chose something like Flower. It's fairly open. It's got pretty good abstractions. As we go through the code, you'll kind of get an idea of why it's fairly well designed for that kind of work. So before we get into it, any other questions or any like initial questions that we have before I start on this part, which is our kind of hello world situation with Flower? No? All right. So this what we're going to be doing is we're going to be doing one of the examples from Flower to get familiar with the framework. So the tutorial is based on this specific example, PyTorch centralized to federated. And so this particular example from the Flower website is about showing how you train a model on centralized data set and how you can convert it to work in a federated way with Flower, right? And so we're running a fork from integrate.ai. So I've made a fork on integrate.ai. That's what you would do if you set up using the instructions. And it's to show the behavior with different train and test sets. So that's because if you use the original example that came from Flower, it's basically using the CIFAR10 original CIFAR10 data set. And that's not really pre-split in an easy way for you to do some of the testing that we wanted to show. So we've split the data for us, and then we've got to put it on a specific place. And I've also had to modify the code in order to load the data from a local data set instead of loading it directly from CIFAR10. Right. And then once we finish the section, we'll be able to run kind of non-FL training for data sets. So this is training for just data without, this is running training for without any FL. And then we'll do an FL training just like on duplicate data sets, just to show the mechanics of how it works. It won't really make too much sense. And then we'll be able to also run FL and like different partition data sets to show this IID issue, which we'll be getting into. Right. I think we've gone through this. Make sure all your prerequisites are installed. Everything is running. And the first thing we should do, so when I say it's running, that means all your stuff is installed in your environment. So if I do a poetry shell here, I'll enter the virtual environment that I have configured for the demo. Right. And so let's make sure everybody can see the screen, I assume. So the first step we're going to run is let me double check here. We're just going to run CIFAR-Py. And while it's running, we'll step through the code. Right. So while that's going, so what this is doing is we're loading data that we've already unpacked from data that we've prepared. And this is all the data centralized into one spot so that we can do a train on that CIFAR10. This is the entire CIFAR10 data set. And then we have a test set that we can use to actually do the evaluation. And it's going to train a neural network model. And it's going to do like 20 epochs for the neural network. So we'll take a look at what this is. Let me just maximize this here. And so we can take a look at what is actually happening. So this version that you have here is very close to the version that you would get off Flower. It's just been modified to have data load in a bit of a different way. And so the first thing that's being defined here is basically it's the configuration for a neural network model. That's as it says right here, it's a CNN adapted from one of the PyTorch examples, right? So we're setting up the definition of a model using PyTorch primitives. Then we have a function for loading datasets, and so the dataset loading here is, as you can tell, it's loading has some options here to load other datasets. We'll be going through that. But we're loading the centralized data set here, and we're going to load the test data set, and then it's just logging what it's loading and giving you the data sets back. And these data set primitives are used to be passed to the PyTorch model. Sorry, just give me a second here. Right, and so that's a couple of load functions, and then there is a train function, and so this is the main function that's training the model, right? So in this particular case, we are training we're training a model with a particular loader. We're going to train it locally. We're going to train it for a certain number of epochs. We're going to use a device. My machine is unfortunately a MacBook, so no GPUs for me, so everything trains on a CPU. And here we're just going to do a iteration across our neural network, and that's kind of it. So it's very straightforward in terms of a typical neural network train that's being done with PyTorch. So you'll see code like this that's pretty kind of pretty normal. Then there's a test function that is used to do the evaluation. So taking a device and then loading data and then doing predictions on the test data and then comparing it to the real labels. And in this case, we'll do an accuracy metric as a measure of how good the model is. And this is just the main call. So this here we load our data, we load our test set, we do a neural network, and then we do an evaluation, we do a train, and then we can print out our loss and accuracy. So I guess this is going to it's taking longer than I thought it would. I guess we can just sit down and wait for it to complete. Is there while this is going, like any questions? Oluwafemi, I think you had a question about clickable link. Is a clickable link to what are you looking for? Otherwise, we can wait for these particular rounds to complete, and then we can move forward. Let me see what else we've got. Yeah, we'll just wait for it to complete. So again, like we're doing the thing locally here, no federated learning, right? We're just going to load it, call the train function on the whole data set. And what we're actually really doing, the reason we're doing this is that we want a baseline for the actual performance so that we can compare it with the federated learning case. And we can also compare it with like different partition mechanisms of like a different partitioning when we have different data sets. So I will come back in a second once this is complete, and then we can continue. Shouldn't be long. So Kumar, question, what the different files are, what they do until the training is complete. So the CFAR 10 data set is, so we can look that. We can just boost that up here. So this is the C410 data set, right? And so it's basically a set of images and classes that are being labeled for what, you know, they have 10 classes and a bunch of images, and they all have labels attached to the image class. And so what we're doing here is that we're effectively training, we're basically evaluating how well a model will do based on this data set in order to do a prediction. And so there's going to be one file that's for the training set and one file that's for the test set. We train a model on the training set, and then we take the test set, which is a holdout from the training set, which means it's data that the model has never seen or the training operation has never seen, do the predictions on it, and then we compare with the real labels that are on the CFAR data set. And then we can calculate an accuracy, which is the metric that we're using to determine how good the model is. Does that answer your question, Kumar? Okay. So we're done. So what we have here is that we have an accuracy of 0.6811, right? So basically, an accuracy of 1 would mean that it would get every single label correct, which would likely mean that it's overfitted. So in this case, it's getting an accuracy of 0.68, so it's pretty good, which means like 68% of the time it gets the right label. So now what we would like to do next is, let's see here, what's next? So now let's do the same thing, but we're going to do Federated train. And while these two are happening, I'll explain what's going on with the actual code. So what's happening here is, go back to my slides here. We are in an environment. We're going to run the server side. Right. And so this is the central server that we were talking about earlier that would actually do the federated averaging strategy for the clients. And then we're going to start 2 clients. I haven't started them yet. And what's going to happen here is that both clients are going to load in this case, they're going to load the original CFAR10 data set, the whole thing. So there's going to be 2 clients loading the same data set and then going to a central server in order to train the global model. So basically it's duplicate data, right? So this is just to show the mechanics. So it's not really a legit model in that sense. So, oops, oh, I did not enter my environment. Right, so what's happening now is that if we go to the server, you can see that it's basically sending instructions back and forth from the server to the clients. And it's going to do, I think I did 30 rounds here. So it's going to go back and forth from the server to the client 30 times. And effectively, right. And in this case, it's going to train it's going to train a fewer number of epochs per client. So previously we were training, I believe, a fewer number of epochs per client, but it's going to do multiple rounds. That's basically what's going to happen. And we're going to get 2 clients going, and then we'll just wait for that to finish. And so while this is going, we'll talk about what's going on in the server and the client implementations. So the server implementation is very straightforward. It's basically the Flower provides a basic server for doing this. Flower server that's basically configured for this. And so it's kind of built into Flower. So most of the work's actually being handled by the actual Flower code in this case. And if we look at the client code, this is where it gets more interesting in terms of how you use Flower. So how you use Flower is that Flower provides an abstraction. In this case, this class here, FL client, NumPy client. It's an abstraction for a client that is going to be used to train the federated learning model, right? And so this client here is loading, has some data loaders configured as parameters. And these functions here, get parameters, set parameters, fit, and evaluate. These are all kind of overrides from the NumPy client. And so you would implement CFAR client, subclass it from NumPy client, and implement each one of these methods. So, and then Flower would handle the networking and the protocol between server and client, and would call each one of these functions as needed. So the get parameters function is about basically, given the current model that we've trained, give me the actual parameters to send back to the server. The send parameters, make sure I am not jumping too far ahead here. And nope, we are on track here. And so in the set parameters, this will be called when we get the global model parameters from the server. We would set the local model in order to continue the train effectively, right? So because this way you can train around for a model, send it back to the central server, have it do a federated average, send it back to you, and then pick up, a client would pick up with the new model weights and then continue the training operation. So, and then fit is effectively the training function. And so if we look at the what's happening here, this CFAR train function is the same function that's being that we had originally, right? So that's this function here, right? Except now it's the data that we're doing for. It's the same data that we've done for the centralized training, but we only train one epoch. But otherwise, it's the same training code, right? You're training the same model in the same way, except you are actually going to send those weights back to a central server. And so you can tell in this case, after we call the train, we get the train here will adjust the model. And then we call get parameters here, which takes the model and then takes the weights out of the model and then sends it back to the server. Then we'll do an evaluation, right? And so this evaluate will be called by the server in order to do a as part of the training. It would do an evaluation for each client, and so the server will send an evaluate instruction, and each client will do the evaluate and then return the actual metric that's being used, which is in this case is the accuracy. That's the metric we're going to be used that's being used for this particular model. And so here is the main function when you are running a Flower client, right? So here again, we are just loading data with to get the PyTorch loader basics, like primitives, sorry. We load a model and then we call train on it, right? In this case, but you have to, this is just effectively generating, creating the model, not actually training it. And then we do here's just an initialization function, and then now we can start a client. So in this case, the CFAR client here is the client that I have defined up here. And this is a NumPy client. And so it basically will handle, the base class handles all the initialization and the definition for what the client actually needs to do. So in this case, we're going to start a NumPy client, and we're going to just connect to the server that's running on my machine at port 8080, right? So Flower uses gRPC for its protocol under the covers. So that's how it communicates between client and server, and it defines all the instructions that are needed to go from client to server. Oh, it's still going. So it's a good opportunity to, let's see, well, what round are we at? Unfortunately, I don't think it actually tells me which round it's running. So we might just have to wait a little more. Good time for questions or anything else. Or a break. I would guess you've got maybe 3 to 5 minutes before it's done. unless anybody else has questions. So there's a question about sharing slides. So I believe we can do that after the session's over. The slides are not really kind of prepared for external sharing yet, so we can do that. We can definitely distribute it after the workshop's done. Send it out to everybody. I'm pretty sure we'll sync up with TMLS about how to get that around.
Ron, it looks like we have a raised hand from Madi in the audience.
Sure, what's your question?
Hi, thank you so much for the presentation. I have a quick question about the network architecture that we're using. Is it running asynchronously or synchronously, meaning that we are waiting for the global model to run the iteration, or we just waiting, or just we are running the iteration and we just update the model whenever we get a update from the server?
So it's pretty much asynchronous. So like let me give you an example. Hopefully this will answer your question. So in this case, we have two clients and we have a server.
Right.
If the first client finishes the training model, sends the instruction with the weights back, there is some settings in Flower that waits for a certain number of clients to finish their particular iteration in order to do the averaging before redistributing in order to do the next round. Does that make sense?
Yeah, right, makes sense. Also, I have another question as well. So when we're basically the main idea of federal learning is to train the model without seeing, the raw data of the clients. But the problem is, if you want to define a model, you need to have kind of like access to the distribution. And I was really wondering that, do you utilize some kind of secure multi-party computation to just have a basic idea of the data looks like and then apply it to the model?
That's right. So what you're describing is the EDA step, right? I don't know what data I'm going to train my model on. I don't really have an idea of what it is. I can't see it because it's supposed to be private, and so that's definitely a what's it called? That's definitely an outstanding question that at Integrate, that's what we're working on, right? Like how do we expose like a minimum amount of information from the clients that will help you with your data train, and then at the same time not expose so much that it defeats the purpose of federated learning for the purposes of privacy and security. It's kind of an open question. We've seen different implementations do different things. Like as an example, we're looking at situations where we will have our clients kind of spin up and be able to serve some aggregate information about the data sets, like maybe just tell you some meta information, give you some kind of aggregate values that we're comfortable exposing. We could expose it in a differentially private way, right? To do that, we could do synthetic data. We could do a few different things, and so that's a bit of an open situation. The data, the modeling data science lifecycle in a federated learning context is definitely a little more complicated. Additionally, another good like kind of sidetrack from that is that what we're showing you here is on CFAR10, which is an image data set, right? And image data sets, the good part about it is that you kind of don't need to do any real feature engineering. And so another problem is that you have to ensure all your clients have compatible feature engineered data, right? So if they're not, then you have to deal with it in that case. And then how do you deal with that? How do you coordinate to ensure that the features are compatible across all your different data sets? Also an open problem to discuss. And it's very use case specific, right? It's definitely very use case specific. For us, we're concentrating on kind of the tabular enterprise data situation. So the issues with feature engineering definitely show up. Like they're going to show up much more as a forefront issue than it would with image, kind of like image or more homogeneous data set machine learning.
Exactly. So basically, you're using metadata to synchronize the data across device clients. That scenario.
Well, it's not necessarily you're synchronizing data. We need to make sure that the processing of to get to the features that are going to be inputs, the way you're doing that has to be consistent. Right? It's got to make sense. Otherwise, you can imagine mixing data where some of the features don't really make any sense.
Also, it's possible to ask another question as well.
Sure.
Yeah. So in the scenario you're using Fed average, right? And basically, when the data is non-ID, you cannot run multiple local iterations because the model did not converge to any optimal point. I was wondering, how do you handle this kind of?
Yeah, so you're definitely jumping ahead like 6 slides. It's no problem. But there's like several ways that we are looking at in terms of how to get around the IID issue. Yeah, I mean, it could be as simple as just just slicing off some like identifying the non-IID data and just not including it as part of the model. I think there's a few different approaches that our data scientists are taking a look at. I myself am not like core data science, and so I can't speak to the details of some of these. I can only speak to it at a very high level, but there's definitely approaches and research being done to deal with the IID issue.
Absolutely. Thanks so much.
Sure. Oh, great. So we've our 2 clients are complete, and so clients are complete, and so sorry, I just need to check something. Right. Yeah, and so they're complete. We can look at the server. And so now we have a metric here of 6805. If you remember previously, we had about 0.6811, I think. So it's comparable, right, in this case. Not surprisingly, it's the same data set. We trained it twice, so this accuracy may not actually mean much in this particular case. But that just gives you an idea for the mechanics, right? We did a distributed train between 2 clients, and the server actually kind of finished a train. And usually what would happen here is that the server would save the model or distribute it back to the clients, or the clients themselves already have they may not have the final global model, right? They may have the average weights that were last sent to the model, which may not be the final model at all. Right. Right, so now we'll talk about kind of the ID issue, which is caused by imbalanced data sets. So we'll compare the performance against like different partitions between clients. We're going to use imbalanced like data sets that follow a specific convention. And so let me kind of give an idea here what I mean. So if you look at the data sets that we've prepared, let me look at this one here, 816. Let's say something like this, right? What this is saying is that this fraction 5 here is that we have 2 data sets here, and these are intended for the 2 clients. So you can imagine you have client 1 has trained using train 0, and client 2 has train 1. And what this is saying for fraction 5 is that one of these files has, there's 10 classes in CFAR10. So we're saying here that one of these files for the classes 0, like the first 5 classes, so half the classes that we have categorized, only 5% of the entire data set represents those classes, and the other 95% represents the other classes. So that's for one file. And then for the other file, it's sort of reversed. For the last, let's say classes 6 to 10 would have 5%, and then classes 1 to 10 would have 95%. So it's this data that we've generated to kind of artificially introduce this skew in the data to kind of show the problem, right? And so there's different fractions. There's 5%, like 1, 2, 5, 20, 10%. And so you can play around with the data to get an idea of what can be done. Right. And so what we'll do is that we will do 1 to 5, and yeah, explain that. And we'll compare it against like CFAR, which we ran all the way at the beginning. 6811 is what we had for this run, and we'll compare what happens. So in this case, we'll do the 5% fraction. So here you can just run the server again. Right. And so, and here we can be quite specific about, what did I put in here? Fraction 5, train 0. Let me just cut and paste so I don't make any mistakes. All right, and fraction 5, train 1. Right, and then we'll go through, we'll just wait for the rounds again. That's basically what's happening. So this will be the same thing. Unfortunately, this will probably take about the same amount of time because we want to be fairly consistent in the tests. So it'll probably take another 5 minutes. So also, again, good time for questions or anything else. I'm going to step away for a couple of minutes, and then I'll be right back. Feel free to leave any questions in the chat. I will stop the share in a second, and then I'll rejoin it, and then we can discuss, and then I'll just reshare again once it's finished.
Hey, Ro, we can't hear you.
Sorry. Thank you. Sorry, I was asking, are you referring to the training procedure of if the mean and the variance of the data shards are different? I'm assuming you mean during the training, what happens if the mean and the variance of the, yeah. So that falls under what if the data is not really in fact the same across the different sources? Is that the problem you're referring to, or do you mean within the same training, what happens to each of the batch normalizations?
Yeah, I think that would be a more general case if the data is different. But even in a same data set, if you have different classes, they may have different means.
Yeah.
Yeah.
Yeah, so like that's correct. And then the best practice is prior to the training starting, especially with the deep learning, normalization is a big part of the pre-processing so that the entire data set actually gets normalized to the mean and the variance of the entire population. And it's not within each batch that the normalization happens. Does that answer your question? Yeah.
I think in batch normalization, like the mean and variance gets updated like during training as well. So even if you normalize it, it's still, they could be different, couldn't they?
I mean, it depends on how it's selecting the batch. If it's randomly being selected from the population that it was already normalized by, it should technically not be different because it's the same distribution.
Mm-hmm.
Now, could it happen? Yes, but how likely is it for it to happen? Probably not that likely, and it probably is not going to go through one round of training anyway, so you can probably catch it in the different loss optimizations.
Mm-hmm. Thanks.
Great question.
Great. So looks like it completed. And so in this particular case, when we did our 5% fractional train, we have accuracy here, 6488. If you recall, previously we had something very similar. I think it was 66 something. And when I ran it previously, the full centralized gave me 6875. FL gave me 6456. So that's kind of very close, right? So even with a 5% skew, you've got you still can get the performance for this, at least for this metric, to be comparable. So what we'll do is that we can run a train with just one of the silos. So let's run it on, say, just the train 0 set, which is like one of the client silos, and see what that looks like. Sorry, here my wrong keyboard here. All right, and this, unfortunately, should be a lot less data, so hopefully, or half the data should be less, but I'll let this run. But the number we will get should be about here, right? So when this is completed, you get 4683. And so this kind of just shows you that, like, the federated learning does give you comparable performance. You can compare it with, like, if you only had half the data, that you would get significantly less performance. Right. So yeah, 50%. So we'll let this one run. Any other questions in the meantime? We answered one already. Sorry. So we get, as we said, like 04545, very similar to what I got when I ran the previous one, which is 4683. So we can then do the same thing for the first fraction, and I'll just kick it off, and then we can talk about it if there's anything else. So in this case, it's oops. This case, it's the 1%. So it's even more skew, right? 99% of each class of each file has only half the classes. It's running, so that we'll see what we get on this round. But the last time I ran 6x is pretty much what the centralized model gave me, and the FL would give me 401, which is not great. If you compare it to a single silo just for completeness, you would get this. And so this kind of demonstrates this basically demonstrates this issue, right? Where you have partition class imbalance, non-IED-ness. It's a real issue in federated learning. I put here a couple of links about this. In OpenMind, there's a pretty good example of this about federated credit scoring that shows the non-IED issue. And for a certain amount of skewness, right, it's okay to use fed average, right? So we showed that, like, in the 5%, it's probably working fine. So part of this is actually knowing when it'll work or not work. And I believe somebody asked me a question about, like, what can we do to deal with the situation. And so these are some of the ideas that data scientists are working on now, which is, adaptive federated averaging or personalized federated learning. I believe personalized federated learning is about basically on the local side, we only use the data that is most relevant, that would most contribute towards a good global model, and omit the data that would just cause problems with the actual global model. And I don't remember what adaptive federated averaging is, but yeah, so there's definitely different techniques on dealing with this particular problem. These are just one of the challenges in federated learning. There's quite a few more. This particular link is a good one to follow. This is a paper on, like, kind of advances open problems. It's a fairly recent paper and talks about kind of the known problems right now in federated learning that people are looking at. It's a good summary of what's happening in the federated learning space. So I want to let this finish so that I can confirm that I'm not kidding with you guys, and we can see what this actually looks like. It's a good opportunity. Again, any other questions about this particular case before we move on to differential privacy? So yeah, Bro put the answer in for the adaptive federated learning, clearly in her wheelhouse more than it is in mine. Right, so accuracy here, 5.9. It's lower, probably not as low as the last time I ran it, but definitely lower. Right, last time I had 401. Double check I actually ran the right one. I did. Maybe I ran more rounds this time, but regardless, it's lower. So yeah, and so that's the issue with the IID. So we've gone over this a little bit, and so now what we can talk about next is privacy preservation, right? Sorry, let me just adjust my screen share here. Oops, sorry. Right, and so what we'll talk about here is federated learning and differential privacy. So frameworks like Flower, are intentionally flexible. So they don't necessarily include differentially private methods, or maybe not yet. They don't include it now. We'll be looking at a library called Opacus, a library for adding differential privacy to PyTorch models. We'll run an example in the non-FL case. So we're not going to show like differential privacy with federated learning because that's actually what we do. We're doing that internally. So these examples won't cover that, but we'll show it in like the non-FL case so you can kind of get an idea of how it runs, affects performance and privacy. And then we'll talk about how this gets added to the FL framework, and which is what we do at Integrate AI. Right, so one slide to kind of describe differential privacy, if you're not familiar with it. So as a quick overview, it gives you a measurable guarantee on your privacy protection of your data, right? So it gives you a way of being able to compare how private, in a sense, your exposure to that data is. So differential privacy adds noise to the results of a computation, like an aggregation or an ML model. The noise that you're being added is controlled by a parameter designated as epsilon. And what you need is a privacy budget, which kind of you have to decide basically. You have to decide upon ahead of time, which relates the risk of your re-identification. So you're trying to relate the risk of somebody possibly being re-identified in the data set that you are doing your processing on. And so the privacy budget kind of accumulates on certain operations, right? So you can imagine if you did a deep differentially private computation and you released a differentially private data set, depending on the computation that you're running, if you do it again on the same data set, you are exposing more information about that data set, and it kind of consumes the privacy budget. And if you had set a specific threshold, once that threshold is exceeded, you technically shouldn't use that data set for that computation anymore, right? And so you have to find ways of what to do in that situation. And so skipping over a whole bunch of details with like DP computations. And again, if exceeding the budget means exceeding the risk that was decided upon. So that's like differential privacy on a slide. I don't know if there's like any questions before we move ahead to the next stage. No? Okay. So the next part is we'll try the Opacus run. So let me double check here. Opacus is a library that adds differential privacy to PyTorch. So we'll run an example. And when it's running, we'll discuss what it's doing. So this particular example is based on Opacus's building image classifier example. So I took that example, which is usually a notebook, and I've tweaked it to run in a console because just to make sure all the dependencies are available and it runs fine. And we'll run like two cases. We'll run it in the case where epsilon is very large, right? And we should get a performance value that's very, we'll get a specific performance value that's basically the baseline that we're going to compare with. And then we can run it again with a smaller epsilon. So we can set an epsilon of like just 1. And we'll compare the value then. So this will spit it up, and we can, let me make sure it ran. Yeah, okay, there it goes. So if you take a look at the actual code that's available, we can go through what it's actually doing. So in this case, it's the same idea. We've modified this particular file to load the data set that we've prepared, so we can train it on like the skewed data sets if you so felt like it. So instead of using the full CFAR10 data set. And in this case, we're also not using the original model that came with the example, which was like a ResNet 18 example. We're using a much simpler model definition that we've defined here, so that it runs faster. Otherwise, this would not complete. So these are, again, a definition of a loader, and for test and train data, again, this net here is the same model that we had here that I used for the federated learning, simple CNN. And so this is like some operations that are just showing as part of the example. The way Opacus works is that it effectively injects code into the optimization step in order to add noise, and that's how it actually works. And so there's some tools for inspecting the model to ensure that it has certain compatibility for the Opacus to actually work when it does the injection. And so this is some details that you can definitely read through later. And what happens here is that first we define an optimizer. This is the optimizer we're defining. We defined our actual metric function, which in this case is accuracy. And then we instantiate the privacy engine from Opacus, right? So this tells us how many epochs we're going to run. This is the target epsilon that we're trying to get towards. Delta is another parameter that's used by in differential privacy. I'm ignoring it for now, but delta basically is part of a relaxation of differential privacy. And then the train function. So in the train function in this case, some details here where it's basically it's doing additional steps on the optimizer for that's being injected by Opacus. And this is just a test function. And it's just then we just do the train here for a certain number of epochs. That's kind of it. So it's relatively straightforward, kind of showing you how to actually integrate Opacus into how to use Opacus with your PyTorch model. So completed. So here we've got accuracies 38, 58, right? And so let me see. Let me run it. Actually, what did I have the epsilon set at here? Oh, yeah, it's set at 50. So I can do it again. And we'll see what we get with a much lower epsilon. So any questions while this is running, since we've gone through the code?
So the main change here was just using the updating optimizer to apply the differential privacy here.
Yeah, so let's go back to the code here. There's a prediction engine that's here. This is the part. So you have a privacy engine that's part of Opacus, and you can attach and optimize it to the privacy engine. And I believe the privacy engine here basically kind of injects its code into the optimizer steps. And you do still have to make modifications here in terms of how the optimizer needs to be called. I'm not super familiar with the details here, but it's not a complete like blind insertion, but it's pretty close, right? Like Opacus handles a lot of the heavy lifting.
Thank you.
Right. So it's lower now, 32. Right. And so from 38. And so you can see that like for some cases that you don't lose a lot of accuracy by lowering your particular, by having a much more private value. So different things affect depending on what you're doing, your differential privacy may not cost you that much. But the part that's important is actually how to actually determine what your privacy budget is supposed to be. Right, so we can talk about Opacus and Flowers. So we can imagine now like we have DP on Opacus and then we have FL. You can figure out how to actually merge them together so we can control the privacy for a federated training model. You can have the privacy be controlled at the central service, or you can have the differential privacy done at the local client so that the local client is, the weights are being shared are differentially private, so different ways of doing it. So now in practice, differential privacy, the open problem really in differential privacy is how to relate the privacy budget to the use of the model or the use case, right? So this is like saying, okay, I give you a differential privacy of 1.0 for this data set or your model or whatever it's doing. What does that even mean? Like, how does that mean? How does that relate to a real use case? How does somebody make a decision about what differential, like what your epsilon is supposed to be and whether I can afford to do it? Another problem is that, let's say you exceed the budget, what can you do, right? Like, what are the options of dealing with that? Does that mean you have to retrain? If you retrain, can you retrain on overlapping data? If you retrain on overlapping data, that kind of violates some of the privacy protections that you just put in place, which means you would have to retrain on completely separate data, and then it may not be as useful. And so that's kind of a big challenge, and that's one of the challenges that we're tackling, which is like making it meaningful and then being able to track the actual budget expense towards something that is meaningful. Right. Before we move on to the next section, any like outstanding questions, anything like that? Okay. Right. So originally, like we had this idea of like having a kind of a group discussion, and so maybe it might be best to determine like how many people want to do or interested in this, and then because it's going to be a bit of a longer thing, and there's about 30 of us here, so there'll be a few groups, and if you're interested, we can put you in the group. If not, we can let you go early, give you some extra material to think about. Before that, I will. So if you choose to stay for the particular for this larger kind of like group discussion, I'd love to have your input because it's going to be an interesting discussion about like some of a more realistic problem with federated learning rather than kind of these toy examples that we're talking about. So I will post, like, if you are planning on leaving, here is an kind of a survey for after. I encourage you to stick around, because after that we'll show you like what integrate AI is doing and how we think about it and what we have. If that makes sense. Sorry, give me a second. Right. So yeah, if you are interested, so this is what the group chat will be about. It's sort of like you break up into the groups. We're gonna have some groups, and you're gonna have a group leader in each group, and we're gonna talk about an FL system geared towards tabular enterprise data, and that's kind of the activity. So let's say you have different organizations, you want to train, like you want to do FL on a global model, like what are the kind of use cases could you come up with, right? And then I've got some things here about authentication, coordination, monitoring, networking. So these are about like these are the kind of the kind of factors that you have to take into account when you want to build an enterprise FL system. So like authentication, how do we authenticate people and their data sets? How do we coordinate, right? Like you see in Flower, like what I just described, we have to start a server and then we start clients. How do we ensure, like, are we going to call everybody on the phone to spin up clients in order to do the FL? Like, how does that work? Monitoring, how do we know what's happening? How do we detect skew in data sets without exposing private data sets? So that was back to the problem of the EDA problem. Networking, this has to work over the internet. So how do you secure it, right? deployment. How do you run all of this? Where does it run, right? Like, what are the kind of things that you need to do that? And then privacy and security, right? Like, what other privacy security concerns do you have beyond like differential privacy, right? Like you want to add on top of the model in order to keep it secure and private. Right? So I think if you're interested, stick your hands up, and then we can do a room. If if participants would rather not, it's no problem. We can move on to kind of the demo. If that makes sense. Yeah. Okay. So then let's skip that. So let's talk about, like, Ro, do you want to show what we got? Like, you open to doing that?
Sure. Sorry, I didn't get from, is the silence a sign of people not wanting to participate? Is that what we're taking?
Oh yeah, I'm just checking. I asked and I was like, oh, just put your hands up if you want to stay. If not, welcome to kind of end a little early. Otherwise, like, we can go through what we got.
Sure.
For those choosing to stay.
So are we right that people don't want to participate in the discussion?
Yeah, it doesn't, I don't think.
Okay, sounds good. Okay, cool. Then let's go quickly through the IAI demo. We have an early access program that we would love for people who are interested to trying out our platform to sign up. The link of it will be shared after this session. Okay, let me bring up, I'm just gonna run quickly through our demo. Now that you've seen a few frameworks of how federated learning works, I just wanna walk you through how we are thinking about solving some of these challenges. We at Integrate have created an end-to-end framework, essentially, that allows a user to be able to train a federated learning system without having to set up all the individual pieces themselves. The thing that we're focusing on is mainly 4 pillars. One is the end-to-end usability. So all the great questions that popped out around being able to see some bits of the data, being able to understand what the data contains, how it can be normalized, and like what it can be used for, as well as like a privacy element. The thing about privacy is there are a lot of hip words being thrown around with like differential privacy, homomorphic encryption, and all of that good jazz, but how that actually connects to what a user wants and needs, and what an officer, like a privacy officer, needs to see to feel good that this participation is not going against any regulations. Those are the types of things we're trying to answer, of like, we are providing these tools, we're providing differential privacy, but helping a user understand what that actually means in their context. The other piece that we're really focused on is observability of a system, meaning what does a user need to be able to see to feel like they understand what their model is learning from across the network. The last but not least is the whole conversation we had about what happens when data is not IID, and therefore not all of the participating nodes actually contain either relevant or good information. How does a central server tackle that? So those are the 4 pillars of differentiation between what you saw today and what our product offers. I'm just going to quickly walk you through our system. This is where the central server essentially lies. This is where the data owners and the person who is in charge of running the training gets to set up the environments. I have mimicked the different data silos in my Bash environment, where I've set up our client software that essentially gets connected to the server and allows the participation of the different data sets for training. And let's just create a session together. So all of those things that Ron walked you through tonight, we're essentially doing something similar, but through the II platform here. I'm just going to create one session. You can see that you can enter model config here versus in code that Ron was showing. I'm just going to bring over our default one for a demo. Bear in mind that information around differential privacy parameters can be entered here. What type of model you want to use can get entered here. But for now, let's just stick with the test. Also select from all the participating data sets in the network. There's also a portion that you can go through and understand what is available in these data sets. Once you have that in and you have set up your model configuration, you can create the session. And once the session is created, there is a session ID that each of the client softwares can use to get connected to this training session. Before I enter that, I just want to say that there is an installation process for the software that happens once. And once that's done, I'm just gonna essentially give permission to this session ID to get connected to these client softwares that we have. And then I'm ready to start the training. I can start the session where it was successfully started. And all I need to do is to run the train command here. And once that happens, the system sets up the infrastructure for the central server to train. And the user can see what's happening in each of the batch trainings. The loss gets communicated back and forth. And once the training is done, the user can go in and see essentially what was the loss on the test set of each of those silos, what silos participated, what was the accuracy. So a lot of these things are now centralized. And if a user cares about being able to use this, they can use the model through our client software. So this is me asking for the model that was trained for one of the training sessions to make a prediction on the test set that I had. And that's happening here. And it was essentially a image classification job, similar to what you were doing during this demo. And this is the information that has come back. So someone can take this and use this in their deployment mode. Again, we have an early access program that we're giving access to our software from, and we're happy to have anyone join in. So feel free to go to the link, and we would love to hear from you. With that, we had left actually a lot of time to go through the discussion, given that that's not happening. We're happy to give you time back. Thank you for participating and joining us tonight. If there is no more things to be discussed, we're happy to give everyone an hour back. Thanks for participating, people. Faraz, do we hand over to you? Do you take from here?
Yes, I do. Yeah. Thank you for the great workshop. I see all the fantastic questions that have come in. So thank you so much, team. And thank you everyone for attending this workshop.